Good afternoon. I'm Ying Li, a PhD student from Beijing Normal University. Today, my talk is the metallicity distribution in the LMC and SMC based on the Tip-RGB. My collaborators are Beijing and Yiren. First, we started some works for the gradients. In their works, they give the negative gradients in the LMC and the SMC, and some of their works give the range from the galactic center. However, their radius is quite short, so is it possible to obtain the metallicity gradient that is further away? By chance, we get the catalog from Ren's work in 2021. They removing the foreground dwarf stars by their outward branch in the near-infrared color and color diagram with the 2-mass photometry as well as the Gaia measurements of proper motion and parallax. And they identify the red supergiants from the location in the color magnitude diagram of the member stars. As a result, they established the most complete sample of red supergiants in the LMC and the SMC. Use their catalog, we can get the position of the Tip-RGB clearly. The tip of the right giant branch is a sharp cutoff on the color magnitude diagram occurring at the bright end of the right giant branch. Barbie et al. In 2000 point out that the advantage of using G-K as a metallicity indicator is insensitive to stellar reddening. Belazini et al. In the 2004 give some connections between the Tip-RGB magnitude in the I, G, H, and K band and metallicity. At the same time, Valenti studied the luminosity of the TRGB in J, H, and K band and their dependence on the metallicity. We give the picture is metallicity versus G-K. By Valenti and Belazini. So if we get the G-K of the Tip-RGB, we can analyze the metallicity gradients in the LMC and SMC. We use the catalog from Ren's work in 2021. This is the CMD from their work. In order to destroy the continuation of the Tip-RGB by other types of stars, we select the stars within the boundary conditions. So in the LMC, our sample have 9,285 stars and 49,695 stars in the LMC. Then we use the Voronoi method to get the position of the Tip-RGB. This is an example for the LMC. The first panel is the color magnitude diagram of the member stars. And the panel B is probability density function of the member stars. And the right line shows the K band versus G-K relation of the ridge line. In the C panel, the black dashed dot line shows the PDF versus G-K relation, and the black solid line shows the PDF versus K band relation. The right dashed dot line on the right and left mark the bright and fun ends of the Tip-RGB. And the middle one for the true position of the Tip-RGB in the LMC. And the last is the 3D density distribution of the member stars. So from this process, we can use the Voronoi method to get the Tip-RGB position. And for the LMC, the K band is 12.01 and the G-K is 1.003. And then we analyze the error by the bootstrap method. We set the parameter as no relaxation sampling, and use 80% of the total member in use the PN method to get the precision of the TRGB, and repeat this process 2,000 times. So we can get the expected value and standard deviation by the Gaussian fitting. Within one standard deviation are selected to fit key band. Well, in this picture, there are two Gaussian shape. We choose the one where the area is larger in within 3 sigma. And we use the PN method and the bootstrap sampling method to get the location of TRGB in the LMC and the SMC. And our work result is the same as the Ren's work. In order to analyze the metallicity gradients, we need to divide the galaxy to many bins. So we use the Voronoi bin to divide the galaxy to many bins. The Voronoi tessellation is the method of spectral segmentation. This method is useful in the astronomy, such as image processing, adaptive smoothing, segmentation, signal-to-noise ratio balance, and so on. In our work, in the first step, we divide the whole galaxy to many pixels. For the LMC, we set the range 0.3 degree times 0.3 degree. So there are many same size pixel in the LMC. And then we set the target member we want in each bin. Such as LMC, we want 300 members in each bin. Such as this bin, we want there are 300 stars in it. And for the SMC, we want 120 stars in each bin. And if the Voronoi bin, we can get the result is there are 154 bins in the LMC and 70 bins in the SMC. This is an example for the bin number 4 in the LMC. We use the PN method and bootstrap sampling method to get the G minus K and K band in this bin, such as the result is G minus K is 1.03 and the sigma is 0.009, and the K band is 11.859 and the sigma is 0.009. So we can use this process to get the Tip-RGB in each bin, and then we can give the spatial distribution of G minus K and K band in the LMC and SMC. The top panel is the G minus K. G minus K gradually decreasing from the center to the periphery, and the center is bar-like. And in the bottom panel is the K-ling trend. The K-ling trend, the K-band trend increasing from the center to the east is weaker than to the west. And we can see the K-band trend is not as same as the G minus K trend because the K-band is influenced by the vertical depths. Well, in our work, we assume a constant distance of 50 kiloparsec for the LMC. And then we analyze the metallicity gradients in the LMC. We use the Valenti's relationship in the 2004. J minus K equal to 0.3 metallicity plus 1.28. As a result, we get a negative metallicity gradient in each direction of the LMC, and the distance along the bar is 10 to 16 kiloparsec, and the north and south only is 10 to 10 kiloparsec. And for the north, the metallicity gradient is minus 0.006 decks per kiloparsec, and there is the details. This is the spatial distribution of G minus K and K band in the SMC. We can see there is a higher G minus K near 15 degree. It's forming a submarine. We think it could be a star forming region. And the metallicity gradient in the LMC is also a negative it's also a metallicity gradient in each direction of the SMC, and the distance along the bar reaches up to roughly 27 kiloparsec. And the north and south directions extend up only to about 4 kiloparsec. And the north is minus 0.07 decks per kiloparsec. At last is my summary. With the most complete and full sample of the roid member stars so far, this work obtained the Tip-RGB precision of the LMC and the SMC, which agree with previous results. And the LMC and SMC are divided by the Voronoi being. The value of J minus K and K band of each being TRGB are calculated by the PN method, and their uncertainties by the bootstrap sampling. Overall, there is a negative metallicity gradient in each direction of the LMC and the SMC, and the metallicity decreases with the distance from the center. In our work, the farthest distance for LMC is 16 kiloparsec, and for the SMC, the farthest distance is 10 to 27 kiloparsec. The gradient is large from center to 1 kiloparsec, which may be related to the bar structure. That's all. Thank you for your attention.
Hi, great talk. Sorry if I missed it, but can you explain how you're going from J minus K, is that right? J minus K, J minus H, whichever one it is, to metallicity? How are you making that relation from the infrared color to the metallicity for your stars?
Okay. We use the relationship from Valenti 2004.
Oh, okay. Thanks.
Oh, thank you for asking.
As far as I see, the metallicity gradient is not very marked, no? I mean, sometimes it's within the error, the decrease in metallicity with distance to the center, no? And they are very small. I mean, the gradient of metallicity. So the question is, how does it compare with the one in the Milky Way? You know, the decrease in metallicity with distance to the center. In the small and the large Magellanic cloud seems not very. Sometimes it's like within the errors.
The error?
The error in the gradient. Okay, we can speak later if.
Sorry. I can't understand. Can you repeat?
Yeah. So I mean that the gradient in the metallicity is very small, no? In the large Magellanic cloud and small Magellanic cloud. So the question is how does it compare with the one in the Milky Way?